This is Scott. I'm going to go ahead and start.
Oh, okay. Sorry,
We're
Scott.
going to go in, I'll go through relatively quickly because I think you really want to see some of the cool stuff Jeremy's going to show you. But it's going to build, and what I'm going to present is going to build on what Julie presented, taking a little bit different approach to it, and also answering one of your questions about repair, hopefully, as we get through it. So what do we mean by resilience? And Julie did a good job of covering some of the high level aspects of resilience and even getting into some of the details. But there's an industry statement on resilience that many professional organizations have signed on to. And the essence is resilience is the ability to resist, recover, and adapt from extreme events or changes. But what does it mean in practice? You see here the picture that this house more or less resisted the hurricane in this case. But what do we mean by this in practice? So for resistance, I've got a simpler version of the plot, the resilience plot that Julie showed. Resist is really what we think of as the typical design objective. That is, an event occurs and we limit the damage to some amount. The question is how much damage? And we can see on the plot here, I've labeled resist as this loss of functionality. That's your resistance. How much functionality do you lose, ranging from 0 to a complete loss of the system. So recovery is the newer concept, I would say, from that resilience is introducing, and functional recovery is exactly the term that's being used. So how long until we're back in service? And what does it cost to do that? And what level of use? Because functionality isn't necessarily full recovery. You may be able to get enough functionality out of your building at a much lower level below full recovery. That is, it might be a shelter in place, which isn't really full recovery. There's still repairs that need to be done, systems that need to be repaired. But you're able to shelter in place. Maybe it's something even less than that, and maybe it's more than that to make the building functional. So that's a very important question of what level of use is required out of a building, in what time frame, and how much does it cost? And finally, adapt. And this really fits very well into Julie's last response to the question is, how do you deal with changing conditions? I've got it shown here on the chart is improving the functionality before an earthquake, but that's really a little simplification of the problem. It's more than that. What do you do about use and occupancy? After all, we don't want to design buildings like the strip mall down the street that's 20 years and we tear it down and build something new. On the other hand, in 20 years, we might not need that strip mall anymore. We're all seeing serious problems with maybe the return of retail in a lot of cities, maybe even office space, as if work from home becomes more prevalent. What do we do with those spaces? So the ability to change them to a different use, and we're seeing that now with retail spaces being converted into healthcare facilities. Now, obviously you can't convert a strip mall into a hospital, but you can convert it into doctors' offices, clinics, and so on. So how do you design your building so it's able to be adapted to future uses if you want that building to last 100 years? What about the hazards? The hazards are changing. We've seen that with the floods in particular. Our knowledge of other hazards such as seismic are constantly evolving. As anyone who has dealt with ASC 7 seismic knows, the biggest complaint is the map's changing every single cycle. That's based on new knowledge, but it doesn't make it easier for the designer. You have to, in some ways, if you want a resilient building, you have to anticipate future changes in the hazards and incorporate that into your design. And of course, climate change being a big part of that. Not only in terms of the hazards, the typical hazards we think of as flood from rain or more severe weather events, sea level rise is an issue. Also, the changes just in climate in terms of the building itself. Julie talked a little bit about what do you do when the power is out? Well, if the climate is warmer, that becomes maybe even more of an issue. Or if the climate is colder, it might become more of an issue. Some places might get colder average temperatures. So you have to consider that as well if you want a truly resilient building. But at what level do you consider it? For which buildings? Not every building needs to be fully resilient. So we talk a little bit about improving resilience today. I'm going to just go through a couple of things that you can do today to improve resilience without any of the more advanced ideas or more guidelines, and most of them are of little cost or little to no cost. So enhancing and repairing concrete members, we'll talk about that, and that's really goes directly to the repair question that came up during the chat. Mix design is a big part of it. With proper mix design, you can get very different performance out of your concrete than a standard mix that might be used. You can use fiber reinforcement. These are the three things I'm going to talk about. There are others ways you can improve resilience. And each of these can address both resistance to the hazards, recovery after an event, and adaptation of the structure. So one way to repair structures is to add external confinement. So you're going to increase strength and ductility if you do this properly. Typically, you see it as seismic retrofit, that is a building that is not capable of withstanding an earthquake. The additional confinement that you provide with a steel jacket or the fiber wrap will increase the ductility, the strength and ductility of the section by adding confinement, and therefore improve the earthquake performance. You also can repair damage with this. You see it very commonly in marine structures where they use external confinement, typically a fiberglass jacket that's filled with grout, to account for damage to the pilings due to the exposure to the marine environment. And it's also for change of use. Suppose you want to add an additional story or two to a building. Well, one way you might be able to get the capacity out of your columns is to increase the confinement and therefore the capacity of the columns, which would allow you to add the additional load. And note that this can be done before an event, that is in terms of the seismic retrofit to increase capacity or to change of use or to repair damage, or it can be after an event, again, repairing damage due to an earthquake or another event, so that you don't have to tear down the structure. You're able to go ahead and reuse that structure. Crack repair is another obvious one. We all know what happens when you get cracks in concrete. You get water inside and you damage the concrete. So crack repair, whether it's epoxy mortar, concrete repairs, or an epoxy concrete, just for some examples, is a way to help prevent further damage. That is, you're increasing the life and therefore the resistance of your structure, preventing corrosion, hopefully internally, and increasing resilience. So again, it's a way to, in an existing building, to extend the life and get a more resilient structure because of that. Mixed design, and for new structures, maybe the most important thing you can do to address a lot of issues, not just resilience, but sustainability as well. You can use concepts such as Portland lime cement or other supplemental cementitious materials. Of course, there's other admixtures you can put in the design, mixed design, that will change the performance of the concrete and give you a more resilient or sustainable mixed design. Obviously, you can increase the strength doing this. You can get increased durability, both of which lead directly to better resilience. You can also lower the carbon footprint by, instead of using Portland cement, by using either Portland limestone cement or supplemental cementitious material, fly ash, slag, silica fume, etc. So this is a very easy way, and in most cases, little or no cost way to improve the resilience of your structures. Fiber reinforcement might be another way. Again, the benefits of fiber reinforcement: you can get increased ductility. You're going to control cracking, improve the durability and toughness of your building or structure, improve the freeze-thaw behavior, and reduce shrinkage effects. So these are all ways in which today, using current technology and current building codes, you can still increase the resilience of your structures without going to designing for higher loads or a performance-based design. So I'm going to talk a little bit, having just mentioned, about performance-based design. Obviously, as Julie mentioned, code design is generally life safety. That is, it's not intended to preserve the function of a building after an event. It's intended to prevent loss of life during the event. There's nothing that prevents you from choosing a performance level beyond code compliance and then designing to achieve the desired performance. The difficulty here is the owner needs to agree to it. The owner needs to want that higher performance level. You will see owners that do that. You see it, of course, in the healthcare industry. Hospitals are required, but even a lot of them go beyond code to try to keep continued operation after an event. You also see it in certain industries. The semiconductor manufacturers is a great example, is that the cost of the building is very little to them as compared to the cost of the equipment and the product. So they would rather have a building that meets a much higher performance standard, even though it costs more, because downtime after an event is extremely expensive for them. So sometimes owners will choose it. Sometimes they'll be driven by the jurisdiction. But you can then design to achieve the desired performance. Some guidance is available, as Julie mentioned. USRC, US Resiliency Council, uses ASCE 41s. ASD 41 for seismic loads. There's been a lot of work that's gone into that. It's a very detailed guidance on how to achieve specific levels of performance beyond life safety. Immediate occupancy being the most widely used one for hospitals and other critical structures. But further guidance has to be developed, not only for performance-based design for loads other than seismic, but for prescriptive design, because realistically, the vast majority of buildings in the foreseeable future will still be designed using prescriptive design methods. They're not going to go to a full performance-based design with nonlinear analysis and peer review and the rest. So it's very important that we look at developing these guidelines for prescriptive design. And one of the big questions is, what do we mean by resilience? And what do we mean by recovery? How much recovery is needed to achieve a specific level of resilience? And that may vary by building type and occupancy. That is, a residential may have a very different definition of what functionality means than an industrial facility, or, as Julie mentioned, a waste treatment facility. So there's a lot of work that needs to be gone into developing guidelines and standards to allow us to get more resilient designs without having to go the route of a full performance-based design. So for the vast majority of structures. I think I'm going to end with just a little discussion of sustainability and resilience. Julie touched on this, I think, very well. I'm approaching it maybe from the opposite standpoint, but arriving at the same destination. These are not the same thing. And the biggest challenge, I think, in resilience, developing resilience standards and guidelines, is there's a group that would love to see resilience and sustainability mean the same thing. So to get resilience, you do green building design. I would say that sustainability is a component of resilience. That is, increasing sustainability may lead to better resilience. And again, Julie touched on this, so I'm very happy we're covering some of the same ground, because I think it's very important. If you need less energy to run your building, then obviously you need less energy recovery after an event to keep your building going. The same with water. Some of the options you can pick to make a more sustainable building also give you better resilience. The reason I say sustainability is a component is because when you look at a building, there are buildings that resilience is important and sustainability is not important for those buildings. That's not the opposite. It's not true. There's no building where sustainability is important, but you can ignore resilience. And the example we give that I've used in other cases is NORAD. It really doesn't matter how much energy it uses. It doesn't matter what that it's using renewable energy or not. The idea is it cannot be down ever for any reason. It's a resilient question and not a sustainability question. If you can get some sustainability, that's great, but it's really not driving the design. Most buildings, of course, are going to be a combination. You want a resilient building, and you also want sustainability as much as you can get and still achieve the level of resilience you want. And again, for a lot of buildings, they're very complementary. And I guess I'll end with the idea that the most sustainable structure is one that lasts. If you landfill your building after 20 years, it is not sustainable. I don't care what LEED rating you have, how much renewable energy you use. It is not a sustainable structure if it doesn't last. I'll put up my contact information for a minute if anyone would like to take it down. And I guess then I'll stop sharing and turn it over to Jeremy.